All right, this next theorem, Fermat's theorem on local extrema, says that if f of c is a local extrema, then f of c is a critical point of f. So remember that in the case of local extrema, we know that essentially it means we have something that looks like a sharp, jagged peak, maybe a smooth, rounded peak, or a sharp valley, or a smooth and rounded valley. These are examples of local extrema. Here we have local maxes. Here we have local minimum. And then for the ones that have sharp, jagged peaks, f prime does not exist. Where it's smooth and rounded, f prime is equal to 0 at that location. So, example 5, theorem 2 says that if f of c is a local extrema, so that means we have one of these four scenarios, one of these four shapes, then f of c has to be a critical point. Well, what do we know about critical points? Critical points are where the first derivative either does not exist or equals 0. So clearly that has to be true. Those are the only possibilities here. So now, example 5 says, is the converse of the above theorem true? In other words, if we switch it around, does every critical point of f yield a minimum or a maximum? So the answer here is no. No. What's an example? So for example, we can take the function x cubed. X cubed has a critical point at x equals 0. And if we graph x cubed, we see that it looks something like this. So right here at x equals 0, it flattens out. There's a horizontal tangent line right there. But if we surround this point with a little local neighborhood, a small open set, notice that this point here can't be a local minimum because any amount we move to the left, no matter how small we make this little interval, it's always going to include a value over here, which all of these are less than this y value here. Similarly, on the right-hand side, for our little open set, we try to surround our point. The y values on this side are necessarily larger than this point here. So there are both, there are always going to be both points that have a larger y value or in the smaller y value on any open set that is centered at x equals 0. Even if we shrink the open set to make it very small, it's always going to contain 2 points on either side, which one will be negative, one will be positive. Negative is always less than 0, and a positive is always greater than 0. Therefore, that point at x equals 0, this critical point, does not represent the location of any local extrema. The graph simply flattens out for a moment. So no, not every critical point yields a maximum or a minimum.